So let me introduce you to my work with a bit of context and motivation. As you all know, particles have various origins, either natural or anthropogenic, including marine, agriculture, transport, industry, and residential. So these different sources will release primary emissions of aerosol and gaseous precursors in the atmosphere that will undergo physicochemical transformation, including nucleation or condensation and coagulation, react with atmospheric oxidant on the particular meteorological composition to form secondary aerosols. These secondary aerosols, with increasing residential time, will be removed from the atmosphere, either through wet or dry deposition. So what is important in the context of this research is that freshly emitted particles from these direct sources are generally of less complex chemical composition, as you can see in the figures here. And for example, for the marine aerosols, you will have particles mainly composed of sodium and chloride or magnesium and chloride. So during their transport in the atmosphere, while they undergo reactions and transformation, they become more complex in composition through their aging process. You will have, for example, in the same case of a marine aerosol, a marine particle in this case, a more complex in terms of composition particle with sodium chloride, magnesium chloride, and sodium nitrate. So this allows me to introduce you the concept of the mixing state, which is the distribution of chemical elements across a particle in the population of aerosols. The change in this mixing state will have a considerable effect on particle radiative and hygroscopic properties, thus also on climate. So what is the motivation of this job? It is to study the evolution of the particle composition and mixing state during PM pollution events, and particularly in the Great Dunkerque area. So in the next part of this presentation, I will be talking about the materials and methodology deployed for this research. And also in the result section, I will talk about the particle composition and mixing state, therefore chemical diversity during pollution events in the Great Dunkerque area. So the Great Dunkerque area is a highly industrialized and urbanized agglomeration located in the northern France region. In the figure, this map shows the Great Dunkerque area, where you can see urban or residentials in brown, located nearby industrial areas in violet. And this is surrounded by several farmlands and agricultural sections in green. So this city is characterized by the high and dense traffic network due to this location nearby important countries and cities such as London, Brussels, and Amsterdam. So in the record, the Hauts-de-France region, the Northern France region, is also characterized by frequent exceedance of daily WHO PM10 thresholds. And as you can see, for example, from 2014 to 2010, we have in average more than 35 PM10 pollution days recorded in the city, in the region. So the PM pollution is a very important matter for this region and for the Great Dunkerque area. That's why we decided to investigate more what were the characteristics of the PM10 pollution days in the Great Dunkerque area by choosing 3 PM monitoring stations, one nearby urban installation, another one nearby industrial installation, and one located at the suburban site in the bottom of Dunkerque. So from 2018 to 2020, we recorded 76 pollution days out of 1,096 days analyzed. I recall here that a PM10 pollution day is defined as a daily PM10, a daily mean PM10 above 45 microgram per cubic meter according to WHO. So from these 76 pollution days, you will have most of them are recorded in late winter and spring. Most of them are local, identified across the agglomeration, and most of the local pollution they are observed at one station, mainly in the industrial one, highlighting the importance of industrial activities for this region. So in terms of the duration of the plume, we classified the plumes according to the duration 1, 2, 3, and more than 3 days. We observed that 75% of these pollution events are what we call pollution events, which means that they lasted at least 2 consecutive days. These are the pollution events that we will study in this research. So we deployed a trailer at the rooftop of the University of Littoral Coast, located inside the city, in order to monitor simultaneously meteorological parameters, particle phase parameters with SMPS and OPC, and atmospheric dynamics. And together with particle sampling that was performed using a homemade two-stage rotative cascade impactor named TRAPS that allowed sampling of coarse and fine aerosols and particles for. So the principle of the cascade impactor is detailed in another article, but basically you can collect several particle samples on different substrate on the same plate, impaction plate. So the particles are analyzed using an electron microscope. We perform automated detection, particle detection and chemical analyzing using EDX. So each analyzed particle will provide an EDX spectrum, as you can see here in this figure, and all the particle analyzed will be classified using a program from R, which is hierarchical clustering on principal component. So we will classify the particle into seven particle type, including carbonaceous, S-rich, NR-rich, CR-rich, SCl-rich, metals, and another group that sums up all other particles that were not classified. So during this study, 28,000 individual particles were analyzed and classified, and then allowed us to calculate what we call the mixing state index. It is a ratio, an affine ratio between the average particle diversity, which is the average effective number of elements in each particle, on the population diversity, which is the effective number of elements in the bulk population. What does it mean in real? When you have a mixing state index, T equal to 0, it means that in the population of particles you have, they are mainly externally mixed. You have an external mixture, which means that each particle is made of a single element. However, when you have a mixing state equal to 1, it means that all the species, all the elements present in the population are present at the same proportion in the particle. The reality is that the real world mixture is different. You have both internally mixed and externally mixed particles. So we will see now how this index evolved during the particles we collected during PM events in Dunkerque. So for that, in the results section, we deployed a mixtape campaign. As I said before, the campaign aimed at studying mixing state of particles during pollution events in Dunkerque. So during the 9 months of the campaign from January to September 2021, 5 pollution events were studied that covered 11 PM10 pollution days, and 29 hourly samples were collected. I have to say that only the fine stage particle analyzed are presented in this study. We can have a discussion for the other stage. So in this figure, I show you the individual particle composition and mixing state index of the 29 samples collected during this event. And you will see that on the top, you have the evolution of the mixing state index and the evolution of the chemical diversities, which the average and the bulk. And in the bottom, you have the evolution of the each sample's particle individual composition, with metals in pink, SEL rich in olive, CA rich in yellow, orange, NR rich in green, S rich in blue, carbonaceous in maroon. And you have the variation of the mixing state index from a full external mixing to a full internal mixing. What we observe is that there is a high variability of particle composition and mixing state index, and it is obvious, as you can see. So after observing this, we also made another observation. If you compare, for example, the sample S7 and S14, you see that they appear similar on the figure. However, when you look at their elemental composition, you have 5 elements for the S7 samples and 8 elements composing the sample, like the NRH type in the sample 14. So with the open eyes, you cannot really make this difference. When you calculate their mixing state index, you see that S7 sample has a mixing state index equal to 0.92, whereas S14 has a mixing state index equal to 0.77. This allows us to say that similar particle type can hide important chemical diversities revealed by the mixing state index. So without looking at their elemental composition, we could have calculated just the mixing state index and make this and highlight these differences. And you can see the difference also by looking at these same images, where the S7 sample is more close to a freshly emitted NRH particle, whereas the S14 sample with more elements is close to a more aged NRH particle. Same observation can be made with carbonaceous. You have S10 and S22 sample. We calculate their mixing state index, which are respectively 0.69 and 0.29. And you have the same images of these two aerosols, like these two particles, where the S10 sample is mainly composed of soot, whereas the S22 sample has mainly organic particles. And with the mixing state index, you can really differentiate these particles without having to look at same image, which is really time consuming. So after acknowledging this, we ask ourselves, we understand that the exploitation of the mixing state index is meaningful only if you can relate it to environmental conditions. So how can the variability of individual particle composition and mixing state be explained? What we did is that we classified our sample according to their pollution level between clean samples and polluted samples, which clean samples collected when the PM threshold, when some concentration were below the PM threshold, and polluted sample above. So what we observe is that you have high and similar variability of the individual particle composition, same as we observed before, and similar variability of individual particle diversity. So the pollution level does not really explain the difference in composition and mixing state value. What else could explain? We did a classification according to the origin of the wind during the particle sampling into marine, urban, and industrial wind sectors. So we make the observation that there is also a high and similar variability of individual particle composition, and also a similar variability in individual particle diversity. Therefore, the local wind direction does not really explain the chemical variability. And this is important because in several researches, we use the origin of the wind as a proxy to discriminate between the sources. So what other parameters can explain individual particle composition and mixing state variability? Then as a bulk, we cannot differentiate that. We decided to make an investigation of the environmental parameters at the hourly scale. Therefore, we just focus on one pollution event that was recorded between March 21st and April 2nd, 2021. So during that PM pollution event, it lasted 2 days. We had the first day where we had an event, a plume that was mainly localized, as you can see in the figure, at the level of the Great Dunkerque area, whereas the second day you have a more large plume that covers the region. So it allows us to say that the first pollution was local, influenced by local emission. And the second day, we had a regional scale pollution influenced by transport. So during this pollution event, we sampled seven samples were collected from S1 to S7 at different periods, as you can see in this figure. So the individual particle composition and mixing state is shown in the figure that you see below. And what we observe is that for the sample collected during the local event, you have different particle type, and what you see is that the mixing state is also close to 0.4, like close to an external mixing. So what we understand is that during the local pollution, you have adding of new individual particles, you have more heterogeneous population, therefore you have a low mixing state index. When you observe the sample collected during the second event, mainly influenced by transport, what you observe is that you have a very high fraction of carbonaceous and NRH particle. Therefore, during the regional pollution event, you have more age individual particles, more homogeneous populations, and more internal mixing. So with the mixing state index, you can discriminate between local sources or local pollution event and from regional pollution event. I will stop here. So for the conclusion, what we did is that we deployed a homemade cascade impactor to sample coarse and fine particles. And then we applied this methodology to study pollution events in Dunkerque. We observed that there were a high variability in particle composition and mixing state. And that variability where like with the use of the mixing state, you can reveal that variability rather than using highly time-consuming techniques such as TSEM-EDX. So with the mixing state index, we can also discriminate between local pollution from regional pollution by associating an external mixing to local pollution and internal mixing to regional pollution. So I say thank you for your attention. I'm just open to listen to your question. I hope you could listen very well to my presentation. Thank you.
Thank you, Suleiman, for a nice talk. Very interesting results about chemical composition for mixing several mixing states in urban environments. Any question to Suleiman from, we have one first from Hamza.
Hi, Suleiman.
Hi.
This is Fatma. How are you?
I'm fine, thank you. Pleased to hear from you.
I'm fine, thanks. So my question is, did you try to put this index into the PMF analysis with other parameters that you made?
You said PMF analysis?
Yes.
Not really, because this index is like we plan to use it as a factor to discriminate between the sources. So it can be used to be applied to different sources from the PMF analysis.
Okay, did you publish that?
No, we didn't do that because we didn't perform chromatographic or ICP-MS analysis in parallel of our sampling.
But you have some metals, as I saw. I mean, they are from EDX.
Yeah, like the metals were analyzed, like all the particle types that was provided in the research were analyzed using EDX. And what we used to segregate them was hierarchical clustering on principal component, which is also a statistical method, not PMF, because we could, the results were not appropriate for the PMF model.
Okay. How many samples do you have?
29 sample exploitable, and 28,000 particles were analyzed.
Yeah, they are not enough for PMS, right?
It depends on the method you use.
Okay, thank you.
You're welcome.
Thank you, Fatma. Any other question to Suleiman? I don't see anything. Thank you again for the nice talk. We can proceed with next speaker here.